Good afternoon, calculus people. Hope you're all having a fantastic day. I'm going to go ahead and get into it. We're going to be talking about inverse functions today. Now, this is a subject we start in Algebra 1, and we go over it again and again and again up through Algebra 2, a little bit of pre-cal, and everything else. So let's go ahead and review everything you've ever learned about inverse functions with example 1, and then we'll actually get into some calculus. First, if f and g are inverse functions, so I'm telling you that g is the inverse of f, then the following two properties hold true. First, g of f of x is all going to kind of implode on itself and give you just x. Same thing with f of g of x. If you plug in g of x into f, then the entire function kind of implodes on itself and just leaves you with x. Also, if a comma b is a point on the inverse, then b comma a is a point on the function. So you just switch the points. So like if 2 comma 3 is a point on the inverse, then 3 comma 2 would be a point on the actual function. Then we get into example 1 here. It says, find the inverse and validate. Well, validate means show that one of these two things happens. Either A or B has to happen. That's our validating. So it's a three-step process here. First, to find the inverse, you know that we switch x and y. So you have y equals x cubed, which is our function. So x equals y cubed. Then we cubed root it, so x to the power of 1/3 is y. So you could say that the inverse f of -1, f to the -1 of x is x to the 1/3, or the cubed root of x, right? Well then, you can validate it. Let's do the point first. Is pretty easy to figure out here. Let's say that you have f of x is x cubed, right? So let's use a point, any point. A good one, let's say 3, for example. If we plug in a 3 for x, we get 3 cubed, which is 3 times 3 times 3, 27, right? So let's say we have 27, and that's 3 cubed. So those are equal. Those are right? And then let's say that we use, for the inverse, f to the -1 of x is x to the 1/3. Then in that case, if we flip those points and say 27 comma 3, then 27 to the 1/3 power, or the cubed root of 27, should be equal to 3. And in this case, it is. Let me clean up this power a little bit. 1/3. Better. So again, this is validated. This is validated by using a point. And then you can validate by plugging one equation into the other. In other words, take f and plug in the inverse. Well, if that's the case, the inverse is x to the 1/3, and you're putting it into x to the 3rd. Well, x to the 1/3 to the 3rd, I mean, that all cancels out to just x to the 1st power. Same way going the other way. F to the -1 of f of x, if you plug in the original into the inverse, you get x cubed inside of the 1/3 power, which again just all simplifies to x. So again, you can validate by a point. If you switch the x and y, then you should have the same point. Or you can validate by plugging in the inverse into the original and seeing if you cancel out to x, and vice versa. And that's pretty much everything you've ever learned about an inverse up until now. So I want to go about this a little bit differently here. To do inverses, this part right here, I don't really like the point that this makes. So I'm actually going to make a point of my own on the notes. And here's how I'm going to say it. Write this down. If g of x is an inverse of f of x, then semicolon, to take a derivative of that, to take a derivative of the inverse, it is going to be 1 over f prime of g of x. Now this example 2 was going to show you how we actually derive this equation. In the book that I have and in the book that I learned out of, it just gives it to you. And honest to goodness, you really don't need to know how to derive it. Once you become a mathematician, if you become a mathematician, fingers crossed, you'll learn how to derive them. And it's not really that complicated of a process. You just take the derivative. You end up using the chain rule because you got to do the derivative of the outside and then the derivative of the inside. It's a little more complicated than I think we need for right now. So I want to say this. If you have to take the derivative of an inverse, it's going to be 1 over f prime of the inverse. You plug the inverse into the derivative of the original, and it's 1 over that. So let me show you what I mean by this. Let's get this out of the way here. Perfect example. Number 3 says, find the derivative of the inverse of f of a for this function when a is 3. All right. So to fill in this guy, first I need to know what the inverse is, and I also need to know what the derivative is, right? Now there's 2 ways you can write this. If you're not using g of x, let's say you just use f to the negative 1 prime of x. Instead of g of x, let's just call it the inverse of f. And then this is prime right here. Then that's going to be 1 over f prime of f to the negative 1 of x. Okay? Now, a couple of things that I want to point out here. It tells me that a is 3. See this a right here? A is 3. And I'm going to go back up to the first here. This is my x value for my inverse. This is my x value for my inverse. Well, if this is x for the inverse, it makes it y for my original. Right? This is the x for my inverse. That makes it my y for the original. So here's what we're going to do. We need to figure out what is f to the negative 1 prime of 3. All right, so to figure that out, I'm going to do 1 over f prime of f to the negative 1 of 3. And that comes straight from right here. All right, 1 over f prime of f to the negative 1 of 3. And from here, let me cover this up. All we have to do is fill this thing in. So come up with the derivative, obviously. Come up with the inverse, obviously. And let's figure out what this thing is going to be. Now, the inverse is probably one of the easier things to do here. Because if 3 is the x value for the inverse, that means that 3 is going to be the y value for my original. And I can come up with the x value out of here. And that's going to be what f to the negative 1 of 3 is. So again, a is the x for the inverse. It's the y for here. So let's set it to y, solve for x, figure out what's missing. Okay? So you can do this with your calculator. You come up with x is 2. So what we're looking at then, f to the negative 1 prime of 3 1 over f prime of 2. F to the negative 1 of 3. This is your x value for the inverse. This is your y value for the original. So that means that the x value for the original will be the y value for the inverse. Now let's figure out what the derivative is. So f prime of x, this is my work, so let me separate this here. F prime of x is going to be 3/4 x squared plus 1. And we need to find f prime of 2. So 3/4, excuse me. 3/4 times 2 squared plus 1. 2 squared is 4. 4 divided by 4 will be nothing, so you've got 3 plus 1. F prime of 2 is 4. So come over here and plug that in. F to the negative 1 prime of 3 is 1 over f prime of 2 is 4. And that's what the question is asking. What is the derivative of the inverse evaluated at A? The derivative of the inverse evaluated at A is 1 over the derivative of the original and the inverse evaluated at A. And that's all there is to it. So it's really once you know the value for the x of the original, which is the y of the inverse, and once you know the derivative, it's a 3-step process. And that's really all there is to it. Okay? Now, let's go to the back. This one may take a little bit longer. These are trig functions, and we're not as comfortable with trig functions as we'd like to be. I get that. That's why we're working with them. Get a little bit more comfortable. Okay. First, right off the bat here, we've got if y equals the sine of x, then the inverse function can be written as sine to the negative 1 of x equals y, or arc sine of x. Arc sine means the inverse sine, right? Or you could just switch x and y. Sine of y equals x. They all mean the same thing. Arc sine is probably the one you're used to hearing most of the time. So I want to graph this for you really quickly. First, it says graph the inverse sine of x equals y. Over here, I'm going to come up with y equals sine of x. And you've got your x value and your y value. I'm going to come up with a t-chart so that we can graph sine of x over here, and then the inverse sine of x over here. Okay, now if you trade your x and y values, you can kind of think of this as an origin reflection, is exactly what it is. So your x and y values are trading off. So let's stick with the big ones here. Let's say we go from 0, pi over 2, 0, pi over 2. What's the next one we can do here? Let's go from pi, let's just go by increments of pi over 2. 3 pi over 2 and 2 pi. So the sine of 0 is 0. The sine of negative pi, or excuse me, the sine of pi over 2 is 1. The sine of pi is 0. The sine of 3 pi over 2 is negative 1. The sine of 2 pi is 0. 0, 0. We'll go to 1 up here, negative 1 down here. 0. Pi over 2 is 1. Pi is 0. 3 pi over 2 is negative 1. And 2 pi is 0. So you get the sine wave, right? That's just a sine wave. That's nothing new to us. And we're going to inverse that over here. So if you notice here, all you're doing is switching x and y. x and y. So you'll have, let me go to 1 here, -1 here, and then let's say from 0, 0, we'll go to 2 pi, pi over 2, 3 pi over 2, 2 pi, 0, 0, 1 here, 1 here. And that is the inverse sine. Now, there is a problem with this one though. There's a problem with this because I can't repeat something that's not a function. So if you notice, this part right here overlaps with this, and this part here overlaps with this, which fails the vertical line test, makes it not a function. And I can't have that. This all has to be a function. So what I'm going to do is get rid of the two little pieces that overlap. Okay? And what I'm going to say is that for only a piece of this will it actually exist. Okay, so I want you to write this down here. Not a function, so restrict it. Restrict it. And I'm going to say that my y value, let me do this in the middle here, my y value has got to be somewhere in between, let's say pi over 2 and 3 pi over 2. Now I could pick any one of those if I wanted to. If I wanted to continue the sine wave down here and go negative pi over 2 to pi over 2, that's fine. But I'm only going to take one piece of this that makes it a function, and I'm going to restrict it. All right? Now, before we actually get into the derivatives of the inverse here, I want you to look at your derivative rules. All right, this is arc sine, arc cosine, and arc tangent. All right, now you see this u here? This u is in the same place as x, but u can be anything. U can be an equation, u can be a number, it can be a variable, it can be anything. So what we're going to say here, the derivative of the inverse of sine is 1 over the square root of 1 minus u squared times the derivative of u with respect to x. Okay? Times the derivative of u with respect to x. Here's what it's going to look like. I'm using sine up here, obviously. So the first thing I want to do is switch to find the inverse. The inverse of y equals sine x. So the inverse of that is going to be x equals sine of y. And then let's take the derivative of that, right? Now what I'm going to show you here is how we come up with this stuff over here. So I'm going to take the derivative of this. I get 1 is equal to cosine y dy dx, right? So I switched the inverse, found the derivative, and here's where things get a little weird. In order to come up with this, we have to go back to a principle we learned in pre-cal. Now, keep in mind, all I'm explaining right here is how we came up with the derivative rules. This is just how we came up with them, not how we use them. How we use them is so much simpler. But I want to do this really quickly. If you remember, sine squared y plus cosine squared y is 1. Sine squared a plus cosine squared a is 1. Right? It's a property. And if we solve for cosine, we get cosine squared y is 1 minus sine squared y. Solve for cosine y, so square root both sides, you get cosine of y is the square root of 1 minus sine squared y. Okay? So from here, what I'm doing is I am taking my cosine squared y, this thing, with the dy dx in front. You know what? I'm going to put a pause on this. I think this is going to do more harm than good. Throwing an audible in here. Forget it. Audible. You don't need to know. You need the derivative rules. They're so much easier to use than they are to explain. I'll explain it to you sometime later when we have more time for this, but this, maybe in class, it's not important. What's important are these. I'm sorry to break down like that, but oh well. What's important is using them, okay? So let's actually use them. So the derivative with respect to t of the arctangent of t squared, that's this guy right here, is going to be equal to 1 over 1 plus. Now you see this u squared right here? U in this case is t squared. Okay, so u is t squared, so it's going to be u squared, which is t squared squared. Du dx, the derivative of u with respect to x. In other words, now that's because it's dx here. Here I'm taking the derivative of this with respect to t. Respect to x, respect to t. Well, that's easy. The derivative of t squared is 2t, which is 2t over t to the fourth plus 1. See what I mean about them being easier to use than they are to explain? All I'm doing is squaring u and then taking its derivative. Square u, take its derivative. That's it. Example 6, the derivative with respect to theta of the arcsine of tangent theta. Here we go, right here, right? That's going to be 1 over, copy my formula, the square root of 1 minus, now u squared, u in this case is tangent, so tangent squared theta, times the derivative of u with, in this case, respect to theta. So the derivative of tangent, secant squared theta. Now the secant squared theta, so secant squared theta, derivative of tangent is secant squared theta, tangent squared tangent theta, which in this case should be good. Multiply, put it on top. Tan squared theta. There's something missing right here. I'm going to correct that in class. I don't want to go back and re-edit and redo the video, but I'm going to correct this in class. Something's missing right here. But using these, so simple. It couldn't be easier. And that's because we have derivative rules for it. Again, I'm sorry about the coming up with the rules, but as long as you know the rules, use them. You don't need to know how we came up with them. I'll tell you later, because I know someone's going to want to know. So we'll tell you later. Okay, have a good day, guys.